Hi everyone. Thanks everybody for joining today. This is Avinash Dalmia. I'm a senior principal application scientist at PerkinElmer. Today I would be presenting on overcoming challenges associated with analysis of pesticide mycotoxins regulated by Colorado State in hemp using a novel LC-MS method with dual ESI and APCI ion source. This slide shows the outline of my presentation. First, I would talk about different lists of pesticides and their action limits in different US states and Canada for hemp and cannabis matrix. Next, I will show you how we analyze some of the non-polar pesticides such as etiadiazole, quintozine, cyhalothrin, methylprenes, and few others using our novel LC-MS method with dual ion source. Next, I would talk about ionization mechanism of non-polar pesticide with APCI ion source. Later on, I would show you how we mitigated hemp matrix effects with LC and MS method optimization to improve method sensitivity. In the end, the rationale of our sample preparation method, which was automated simple solvent extraction with good extraction efficiency, less cost and higher throughput, and we added a number of internal standards which are available from PerkinElmer region kit to improve method accuracy. So different US states and Canada regulate different number of pesticides for hemp matrix. For example, there are regulations for 59 pesticides in Oregon state, 66 pesticides in California, 96 pesticides in Canada, and 102 pesticides in Colorado state for hemp matrix. Even for the same pesticide, the action limits are very different in different US states and Canada. For example, for acygnosyl, the action limit in Oregon state is 2 ppm, 0.1 ppm in California state, and 0.03 ppm in Colorado and Canada. So as the number of pesticides increase and the action limits becomes more stringent, we have to improve our method continuously to analyze a large panel of pesticides with lower detection limits in hemp matrix to meet the new requirements. Therefore, in my presentation, I would be showing you today that how we improved our existing method for 66 pesticides regulated by California state to meet more stringent action limits by Colorado state for 102 pesticides and 5 mycotoxins in hemp matrix. So we are analyzing all the 102 pesticides and 5 mycotoxins with different polarities using an LC-MS system with the dual ESI and APCI ion source. If you use a single source LC-MS system, it takes a long time to exchange ESI with APCI ion source and vice versa. Using our dual ESI and APCI ion source system, we can analyze both polar and non-polar compounds by switching from one source to another very fast. The next slide shows the structure of non-polar pesticides such as methylpredine and cyhalothrin using our heated electrospray ion source in LC-MS system. So next slide shows that we get excellent detection limits for cyhalothrin in hemp. If you look at the structure of this compound, you will notice that this compound has very low proton affinity. It is a non-polar compound, so we had to optimize both our ion source conditions and mobile phase composition to improve detection limits for this compound to meet Colorado state action limits of 0.25 ppm in hemp. Also, in the past, a lot of people have asked me how do we determine our LOQ for different pesticides. So these LOQs, which I'm showing here, were collected by pre-spiking hemp matrix for all the analytes. Also, our LOQ numbers take into account the 10 dilution factor using our sample preparation method. So when we say the LOQ in this case is 0.05 ppm, that means that the hemp extract had a concentration about 10 times lower, about 0.005 ppm when we were measuring this compound using ESI iron source. So we account for both the dilution factor of our sample preparation method, which is 10, and we pre-spike hemp matrix to determine these LOQ numbers. So in this example, we are showing that we get excellent detection limits for methylprene in hemp. If you look at the structure for this compound, it is an oxygenated hydrocarbon. Therefore, this compound was only analyzed using GC-MS-MS in the past. But using our heated electrospray ion source, we can get excellent detection limits. And our method LOQ is 0.1 ppm, which can meet colloidal state action limits of 2 ppm in hemp very easily. So this slide shows the structure of non-polar pesticides analyzed using APCI ion source. If you look at the structure of these compounds, namely etridiazole and quintozine, you will notice that they are non-polar and halogenated, and therefore these compounds were only analyzed using GC-MS-MS in the past. Therefore, I'm very excited to show you the next set of slides because we can analyze these compounds using APCI ion source without the need for GC-MS-MS for this analysis. Etridiazole is another pesticide which is very non-polar and chlorinated. It has very low protein affinity, so you cannot ionize this compound with good efficiency in positive ion mode using both ESI and APCI ion source. Therefore, we are analyzing this compound using APCI ion source in negative ion mode. This slide shows clearly that we get excellent LOQ of 0.01 ppm for this compound, and we can meet very stringent colloidal state action limits of 0.03 ppm in hemp for this compound. So among different non-polar pesticides analyzed using both ESI and APCI ion source in our method, quintozine is the only compound which can only be ionized with APCI ion source. For other compounds, we can ionize all the non-polar compounds using both ESI and APCI ion source. It might be possible that one compound will ionize better with ESI or it will ionize better with APCI ion source. So based on the ionization efficiency, we choose an ion source to analyze that compound. But only for this compound, we do not get any signal with ESI ion source because of its structure. We can only ionize this compound using APCI ion source. And after optimizing our method, we get excellent detection limits of 0.005 ppm in hemp. Also, not only our method is sensitive, but it is also very selective for this compound using APCI ion source. So if you look at the red trace, which is obtained using the blank hemp matrix, you will notice that the blank hemp matrix shows very low signal. It only shows electronic noise. It does not show any matrix interference peak at the retention time of quintozine. And we get excellent signal to noise for quintozine even at a very low level of 0.01 ppm in hemp. So our method is both sensitive and selective for quintozine and other non-polar pesticides using APCI ion source. Next, I would like to talk about the ionization mechanisms of non-polar compounds with APCI ion source. So it is very well known the most common ionization mechanism for different pesticide is called proton abstraction in negative ion mode, which results in deprotonated molecular ions for pesticides with acidic functional groups like fipronil or flutoxonil. For other pesticides, we could not form deep-rooted molecular ions, so we had to determine new ways of ionizing these compounds and new ionization mechanisms. Uh, so, for example, for pesticides such as chloridane, we are forming adduct ions in negative ion mode by anion attachment. For A-signosyl, it gets ionized by electron capture to form odd electron ions, which is very rare. When you ionize these molecules with ESI and APCI ion source, normally you form even electron ions. For pesticides such as etriadiazole and chlorofenpyr, we are ionizing them by dissociative electron capture. So in this mechanism, they capture an electron, which is followed by dissociation into a fragment ion and neutral molecule. Among these different molecules, the ionization mechanism of quintosine is the most interesting and unique. In this case, we believe that oxygen gas captures the electron formed in a coronal discharge region of APCI ion source to form superoxide reagent ion. This superoxide reagent ion reacts further with quintosine molecule to form an ion by loss of a chlorine and addition of oxygen atom. In the literature, sometimes this mechanism is also termed as dissociative electron capture with substitution. So hemp matrix is a very challenging matrix for pesticide analysis. It is a complex matrix. It contains more than 500 different compounds, including more than 100 cannabinoids and 200 terpenes. Some of these cannabinoids and terpenes might be present in ppm to percentage range, and they can get co-extracted with trace level of pesticide during sample preparation method and cause matrix effects or matrix interference when they have same retention time as your pesticide or mycotoxin. So next, I would like to talk about the strategies we deployed to reduce these hemp matrix effects to improve our method sensitivity. So one strategy is to optimize our MS method to reduce matrix interference and thereby improving method sensitivity. So when you see this slide on the left, you will notice that when we use MRM transitions based on the monoisotopic mass of 342 for propiconazole, we see a lot of matrix interference. But when you see on the right, when we use MRM transitions based on M plus 2 isotope of propiconazole, then the red trace shows that the matrix interference is minimized and we can improve our detection limits by a factor of 10. I would like to point out that the MRM transition based on the monoisotopic mass has the best signal in solvent, but the detection limits are poor in the matrix because of the matrix interference. But when we use the MRM transition based on M plus 2 isotope of this molecule, it has 2 chlorine atoms, so we are losing the signal by 30%, but we improve our detection limits because we minimize the matrix interference by a factor of 10. Therefore, by just changing our mass transition, we can improve the detection limits by a factor of 10 for this example. Next, I would like to show an example of endosulfan beta with APCI ion source. So on the left, when we used a fast 6-minute LC gradient for endosulfan beta, we observed 75% ion separation for this compound, and our method could not meet Colorado State action limits of 0.05 ppm for this compound in hemp matrix. But on the right, when we use an optimum 11-minute gradient with our LC method, now we were able to minimize our ion suppression effects. They were almost insignificant. We were able to improve detection limits by a factor of 10. Now our method LOQ is 0.01 ppm and can easily meet Colorado State action limits. Next, we wanted to understand why we were able to reduce these ion suppression effects by just changing our LC method. So what we did was that we collected APCI ion source negative scan data for hemp matrix to determine the retention time for CBDA, which is the main cannabinoid in hemp matrix. This hemp matrix we use had about 6.5% CBDA. So on the left, what you observe is that when we use the fast 6-minute LC gradient method, both endosulfan beta and CBDA co-elute, and therefore CBDA is causing ion suppression effects for endosulfan beta. On the right, when we use an optimum 11-minute LC gradient, then we get base separation of both endosulfan beta and CBDA because their retention times are now different by 0.1 minute. And therefore, this way we were able to reduce ion suppression effects for endosulfan beta just by changing our LC method. In another example, I would like to show you that we just changed the ion source to improve detection limits for one of the pesticides. In the beginning, we were analyzing A-cyclosyl in hemp using ESI ion source. So after carrying out different optimizations of our method, we were getting LOQ of 0.01 ppm. Recently, we tried to measure this compound using APCI ion source, so we were able to improve the detection limits even further, 0.005 ppm. So now our customers can analyze this compound using two different ion sources to improve their confidence in analyzing this compound. In the beginning, I thought that both these methods are equivalent for A-cyclosyl, but as I extended my method for this compound in different hemp matrices, apart from plant matrix, such as concentrate and hemp or CBDA or CBD-based edible products, we are noticing that APCI method is better than ESI ion source method for this compound because it has better sensitivity and has less matrix effects in comparison to ESI ion source method for this compound. This is the example I wanted to show you was for ochratoxin A. The action limits for ochratoxin A are the lowest in Colorado state in comparison to other US states and Canada. The action limits for this compound in hemp in Colorado state are 5 ppb, whereas action limits in other US states and Canada is 20 ppb for this mycotoxins in hemp. So in order to meet lower action limits for ochratoxin in hemp using ESI ion source, we had to optimize both our ion source conditions. And on the left, you can see that we changed our movable phase composition and we were able to increase our signal by a factor of 5 to 7 with the new movable phase. Now our method LOQ of 4 ppb can meet lower Colorado state action limits of 5 ppb for this compound now. Now I'm going to switch gears and I'm going to talk about the sample preparation method we used to analyze both pesticides and mycotoxins from hemp matrix using our LC-MS method. So we could have used any of these 6 different sample preparation methods, but I would like to ask the audience, let's say they have 6 different options, and the criteria for choosing an option is that it has to be simple, faster, cheaper, greener, and can be automated and shows good extraction efficiency for all the compounds. Then I would think that everybody will go with the option which can meet this criteria. So when we looked at all these different sample preparation methods, only simple solvent extraction with ACN extraction met this criteria for sample preparation method to be simple, faster, cheaper, greener, and can be automated with good extraction efficiency. And that's the reason we chose this simple sample preparation method as solvent extraction in our method. So this slide simply shows the different steps in our simple solvent extraction method with overall dilution factor of 10. We grind our hemp sample using Omni homogenizer, and we add acetonitrile solvent to extract pesticides and mycotoxins. We vortex centrifuge and then filter our hemp sample to get the final extract and then spike it with a small amount of internal standard. Now I would like to define some terms. So when you are choosing your sample preparation method and you need to determine how good it is, you have to determine this extraction efficiency. Extraction efficiency is determined by taking the ratio of the signal in pre-spiked extract to post-spiked extract. This slide shows that our sample preparation method shows excellent extraction efficiency for all the 102 pesticides and 5 mycotoxins from hemp matrix in the range of 80 to 120%. If you zoom into the data, you will notice that about 97% of analytes have extraction efficiency, which is very close to 100%. So this slide shows the comparison of extraction efficiency obtained using our solvent extraction sample preparation method with other 3 different sample preparation methods used in the literature for 5 pesticides. Only our simple solvent extraction method shows extraction efficiency close to 100% for all the 5 analytes. For comparison, if you look at the extraction efficiency for one of the pesticides, pyridamine, with the 4 different sample preparation methods, if you use quetches with DSP, the extraction efficiency is 68%. If you use solvent extraction followed by SP and DSP, then extraction efficiency of pyridamine is about 58%. And if you use the solvent extraction followed by evaporation, then you can't even determine your extraction efficiency. That means it's almost close to 0%. Only our simple solvent extraction method gives you an extraction efficiency of 95% for this compound. So if you are losing anywhere from 30% to 90% of this analyte during the sample preparation method using the other 3 different sample preparation methods, that means your method sensitivity and accuracy will be compromised by 30 to 90%. But this will not happen if you use our simple solvent extraction method. So once you have determined the extraction efficiency of your sample preparation method, and if it is good, then the next step is to determine the matrix effects using your sample preparation method. So how do you calculate that? Essentially, you take the difference in signal obtained for an analyte using post-spike extract and the solvent standard, and you divide this number by signal obtained for your analyte in the clean solvent standard. So if your analyte experiences a matrix effect which is less than negative 20%, that means it's uh, experiencing significant ion suppression effects or signal suppression effects. If your analyte shows a matrix effect which is greater than positive 20%, that means they are experiencing significant signal enhancement effects. So this slide shows the hemp matrix effects for different analytes measured with ESI and APCI ion source method as a function of retention time. You will notice that most of the analytes are experiencing signal suppression effects with the ESI ion source and signal enhancement effects with APCI ion source. This is expected because APCI ion source shows less matrix effect in comparison to ESI ion source for different analytes. Also, since hemp matrix is very hydrophobic, and this is expected that the most of the matrix effects are observed for analytes at a high retention time using reverse phase LC columns. So we are adding internal standard solution containing 30 of them in our sample preparation method to improve our method accuracy, because these internal standards can compensate for these hemp matrix effects. These 30 internal standard solution is part of PerkinElmer pesticide reagent kit, which also contains certified pesticide and mycotoxin CRMs and consumable items to prepare your samples. At this point, I would like to define the accuracy, which is taking the ratio of the measured concentration and your spike concentration. So next slide shows that we can improve our method accuracy by compensating for hemp matrix effects by adding internal standards to our sample preparation method. So this is a busy slide. What you will notice that when we don't add internal standards to our method, about 30% of analytes have very poor method accuracy outside the ideal range of 70 to 120%. But when we add internal standards to our method, we get excellent method accuracy in the range of 70 to 120% for all the 102 pesticides and 5 mycotoxins in hemp matrix. If you zoom on the data, you will notice that except for one pesticide, all the other 101 pesticides and 5 mycotoxins have an accuracy in the range of 80 to 120% with the addition of internal standards. Also, as I mentioned earlier in my presentation, we can also both automate our workflow and sample preparation method with Janus Workstation to improve reproducibility, and also we provide cloud connectivity and traceability with our workflow to get you closer to certification. And here's a short video of our automated workflow for pesticide and mycotoxin analysis in hemp matrix using our new product called QSWorks.
PerkinElmer has created a complete end-to-end cannabis testing solution to fully test the pesticide, residue, and cannabinoid testing on cannabis samples to ensure regulatory compliance. Connected through the Simplicity Lab 420 cloud system, this high-throughput solution utilizes the Janus G3 420 workstation, the QSight 420 LC MSMS system, and reagent kits to ensure a reproducible testing solution. Once the cannabis has been received and weighed, samples are fully prepared using the Janus G3 420 workstation. Utilizing standards and reagents from cannabis reagent kits, the Janus G3 420 workstation can process over 100 samples per shift and uses a barcode reader, an 8-tip Verispan arm, MDT gripper, vortex, and centrifuge to autonomously prepare the samples for the QSight 420 LC MSMS system. The samples are then analyzed using the QSight 420 LC MSMS system, and the quality of data is reviewed by the QC manager. Once complete, the results are uploaded to the Simplicity Lab 420 service. Fully connecting all parts of the process through the cloud, the Simplicity Lab 420 service enables complete sample traceability and compliance submission to LIMS or regulatory frameworks such as Metric. PerkinElmer's end-to-end, fully traceable, high-throughput cannabis testing solution will empower you to accurately and reproducibly test cannabis samples.
This next slide shows our method LQ and corridor state action limits for 102 pesticides and 5 mycotoxins in hemp matrix. In each column, the first number shows our method LQ. The number in the bracket shows the Colorado state action limit for that analyte. Number of analytes are marked with star. So those analytes were measured using our APCI ion source method. The analytes which don't have any star to them, they were analyzed using electrospray ion source method. So if you look at the list, you will notice that a number of non-polar pesticides such as methoprene, canoprene, quintozine, etradiazole, and maybe 20 to 25 more analytes were analyzed using GCMSMS in the past. By using our novel LCMSMS method, we can analyze these non-polar pesticides and polar pesticides and mycotoxins using our novel LCMSMS with ESI and APCI ion source. Now our customers don't need GCMSMS for this analysis. Now they need only one scientist, one instrument, one set of consumables, and one sample preparation method to reduce the cost and complexity of the analysis when they want to use our method. In the end, I would like to summarize the key points of my presentation. We developed a novel LCMSMS method with dual APCI and ESI ion source, which can analyze all of the 102 pesticides and 5 mycotoxins regulated by Colorado State to meet their action limits in hemp. We elucidated the ionization mechanism of different non-polar compounds with APCI ion source. Matrix interference and matrix effects were minimized by MS and LC method optimization and by changing the mode of ionization from ESI to APCI ion source for few compounds to improve our method sensitivity. Solvent extraction is a cost-effective sample preparation method which can be automated using our Janus G3 system to achieve high throughput and with excellent extraction efficiency. We added a number of internal standards in our method, which are provided as a part of a PerkinElmer reagent kit to compensate for hemp matrix effects such as ion suppression enhancement to get overall accuracy in the range of 70 to 120%. I would like to thank a number of colleagues and scientists at PerkinElmer and different cannabis testing labs for helpful discussions with them. I would like to thank the audience for their attention, and I'll be glad to take few questions from you.